The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Welcome back to another episode of the podcast. This is another episode I recorded during my week at Rensselaer Polytechnic Institute for the launch of the IBM System One that they deployed on campus. I hosted a panel discussion on the first night, and then I used a podcast studio in the theater in the event venue at Rensselaer that they provided to me, which was very nice of them, to grab various speakers for these one-on-one interviews. A couple weeks ago, we ran an episode that was a discussion with Professor Lin from UC Berkeley. Today, we actually have an interview with a colleague of Professor Lin's, Professor Fang, an assistant professor of mathematics at Duke University and a member of Duke Quantum Center. She was actually a postdoctoral fellow at the Simons Institute for the Theory of Computing, hosted by Professor Lin and Professor Vazirani. So we talk a little bit about her work in the theory of quantum information science, the theoretical advantages of quantum information science algorithms, what the provable sort of basis for those advantages are and may be, and also the need for balancing sort of that theory side of things with practical side of quantum information science. It's a great discussion. We also talk a little bit about her involvement in the Google X Prize for quantum applications as well, which sort of brings all of her interests in the theoretical and practical advantages of quantum computing together. So let's take a listen. I've got a very special guest today. We're here at RPI at the ribbon cutting of the quantum computer that they've installed on campus. And I'm joined by Professor Fang, who's an associate professor of mathematics at Duke. Is that correct? Yes.
Assistant professor.
Excellent. Oh, assistant. Okay. Yeah. I knew it started with an A. Assistant professor at Duke. And thank you for joining me. Could you start by just introducing yourself and talk a little bit about how you got into quantum information science?
Of course. First of all, thank you so much for inviting me. It's my great pleasure to join the podcast. My name is Fang, and I'm a mathematician at Duke University. I'm also a principal investigator at Duke Quantum Center. My research mainly regarding the theoretical aspects of quantum computing as well as quantum simulation. In particular, I do numerical analysis to quantum algorithms.
Excellent. And yeah, so, I mean, that's a really interesting area to me because, in part, there's this kind of tension between provable efficiency or provable advantage in quantum and then this sort of open-ended exploration of what can we do with these machines. So how did you sort of start to get interested in the sort of the algorithm side of things?
Yeah, that's a great question. So actually, I was trained as a mathematician. My PhD is in mathematics. I do have some exposure to quantum problem. I have been working on, my background is in applied and numerical analysis for differential equations. I've been working on Schrodinger equations, now adiabatic dynamics, when Bornheimer approximation no longer holds, how to prove various bounds, things like that. It was not until I went to Berkeley as a more revisiting assistant professor, a postdoc position per se.
Okay, right.
And it's an independent postdoc position at the time. It is, I think, an interesting starting point for me was that I was actually teaching a high-level undergraduate proof-based ordinary differential equation class. So in my class, I motivate different levels of physics. All can be described in differential equations, starting from the Schrodinger equations and classical dynamics, and then we have statistical dynamics, and then we have fluid dynamics. These different regimes of dynamics one can consider in all different levels of physics. And then I said I'm very much interested in quantum, and so on and so forth. So this was like the motivation for my class. And I had a very interesting and super smart undergraduate student, math major. He came to me and he was like, Dee, you mentioned that quantum is where you really love. And I'm attending another quantum class, which is a computer science class. And then he draw me, he want to sort of, undergraduate students sometimes want to impress their instructors.
Right.
So he draw on my board a quantum circuit. And he was like, this is a super cool thing that I learned in my other class. Since you work on quantum, can you give me some more insights from mathematical perspective? I was like, super cool, but I have never seen a quantum circuits before. And then I also heard about this class from various different venues, like Professor Lili at our math department and other folks, graduate students. And then I decided to go and audit the class. The class was taught by Umesh Vazarani at our CS department.
A pretty famous name.
Exactly. And that's precisely the place I guess people want to start. But at the time, I really have no idea what is quantum computing. I think Umesh class really brought me into this.
So when you said you were interested in quantum in your class, you meant from like a purely mathematical perspective.
Yeah, that's right. That's right. I meant like maybe classically say why Bronheimer holds and what condition Bronheimer no longer holds. If it no longer holds, what kind of bonds should we do in order to crack, and what kind of algorithms. Most of the things we do are, say, in quantum chemistry, either you do electronic structure problems or you do the dynamics. Once you have the potential energy surfaces and non-adiabatic dynamic transitions, what can you do with the nuclear part? So I was trying to justify mathematical understanding of all of these different quantum chemistry treatment, and that was what I've been very much interested in. As you see, this is a quantum perspective, but definitely has nothing to do with quantum computing.
And I mean, in that sort of applied mathematics area, is there sort of like like the mathematical modeling that is exact but very, very difficult to work out, and then sort of the classes that are much more approximation based? Is that
exactly. So the motivation, this is actually the precise motivation I would give in my proof-based ordinary differential equation class, is that we have different levels of physics. The fundamental level is really the most first principle per se is our Schrodinger equation. And then we have our particles which we see and ourselves, like our phone and so on and so forth. We give it a force, it have a moment. This is Newtonian's second law. And then if we look at much larger scales, we have the fluid dynamics. How do we send our plane on the sky and so on and so forth. And then in between, there's the statistical mechanics. That's how we describe plasma and so on. Those were so all of these different levels of physics. There are very important mathematical equations, differential equations, and the quantum level is the Schrodinger equation, and the Newtonian level is the ordinary differential equations and the classical dynamics, and then the dynamical systems, and then the statistical mechanics is Boltzmann equations, and then last level we have the Navier-Stokes or the Euler's equations. And the interesting thing is that if you start from the first principle, from the mathematical viewpoint, all of these equations can be linked together by some parameter, sending some parameter either equal to 0 or equal to infinity. And their limiting equation will be the next level. For example, from the Schrodinger equation, if we send the Planck constant goes to 0, we have the classical dynamics. And then from classical dynamics, if we send the number of particles goes to infinity, we will have the Boltzmann equation. And when we have sent the Knudsen number goes to 0, we will get the fluid equations. All of these are very much interesting mathematical problems, like in which sense of the convergence is holds true, and what are the conditions you can justify. And these are like very interesting mathematical problem that people in differential equations have been working on.
And then so you go to Umesh's class and you start to see sort of the quantum information science approach to it. And that's, I mean, is it because it's applying sort of the linear algebra and the power of the Hilbert space in quantum computation that you're able to do more precise calculus, or is it the linkages between those those levels?
That's a great question. So I think what fancy makes me a lot is because I have this picture from a mathematical viewpoint, we know that these different theories are linked together. So if one were able to solve the Schrodinger equation, many-body Schrodinger equation for a molecule, then pretty much you can solve a large class of these problems. What fancy makes me the most about quantum computing is this potential power of us directly simulating a Hamiltonian simulation for the full molecule. We can deal with electron nuclei fully coupled molecule, and that is precisely a Hamiltonian simulation problem. And this is what fascinates me so much, because classically what we always do is to decompose the electrons and the nuclei into two separate procedures, assuming Bohr primary is true and nuclei is moving fairly slowly, and then we try to solve these biggest problems in chemistry and in
like computational chemistry. I mean, the larger the molecule or the problem space, the more you're approximating and the further off you may be from an accurate solution. So if you're trying to link that up to those other higher level models, mathematical models, your error bars are getting bigger and bigger.
Exactly.
So potentially, if you exactly solve the Heisenberg equation for a large molecule, you could scale up from there and get better and better sort of results from the model at larger scales.
Yeah, that's right.
That's super interesting.
Yeah.
And I mean, this is all like sort of in the abstract. What do you ever think about sort of what the practical implications of that kind of leap forward might be? I mean, you think about quantum advantage. There's sort of a theoretical quantum advantage, and then there's a practical quantum advantage. Do you think about maybe what the practical implications will be for that type of breakthrough?
Yeah, sure. I think, of course, from the hardware viewpoint, we definitely need a fault-tolerant quantum computer, very unfortunately, in order to really demonstrate these theoretical advantages. From a theorist viewpoint, by theorist, I mainly mean from an algorithm viewpoint.
Right.
I would say that maybe the theoretical road path, my personal theoretical road path towards a theoretical quantum advantage might be the following. I would say maybe 4 different levels. It doesn't mean that people should work on the next level until they figure out the previous level. I think all the 4 different levels should be worked on simultaneously. So the first level, I would say, is very much theoretical computer science. The flavor is that given any computation problems that people want to ask, it can be anything. It can be your optimization, your machine learning, and your matrix multiplications and differential equations and all different kind of things. And then we ask ourselves that can we prove the upper bounds and lower bound for both classical algorithms and quantum algorithms? And in particular, say the classical algorithm complexity class is interesting discussion. Is the problem in BQP hard? Then we have reasonable believe that this should be classically hard and quantumly easy, and also one can prove that given a computational problem, what is the lower bound? The at least if a classical algorithm needs to fulfill this cost, and then what is the complexity lower bound?
Okay.
And then we look at the quantum side. We want to find a quantum algorithm which we can prove a quantum upper bound within certain parameter. And then we start to ask ourselves, is there any separation between these two? Is the separation exponential, super polynomial? Is it polynomial, or is there no separation at all?
Right.
And then I think this is the first level, and then we will have some candidates. We can then look at the second level, which is for these candidates where there exists a quantum advantage or quantum separation, can we design the best possible algorithm, a fault-tolerant algorithm, as the first step to match all of the possible parameters? It may not just be the system size parameter, which is typically used in the first layer. It can be other parameters, say the precision, the failure probability, and in the phase estimation problems, there can be overlaps and some other, say, mixing time and so on and so forth. So there are various different parameters in the problem. We want to design the algorithm that has the best asymptotic scalings in the sense that when these are either large or either small, and we have these big O notations, this is the best scaling. And we try to prove a quantum lower bound saying that this is the best one can do. And once you can match this upper bound and lower bound, then you can sort of declare victory at this level. And we have the optimal scaling for tolerant quantum algorithm. And then I think the next level is maybe many practitioners would be very much interested in is for the second level, the problem is typically over abstractions of a reality problem. Maybe we just say, okay, it's a S-sparse matrix. It's a K-local Hamiltonian. But from a practitioner's perspective, what is the concrete H? The Hamiltonian. What is a concrete matrix? In say, an optimization problem or in a physics problem, you want to look at maybe a particular molecule. People are talking about for MoCo, I think, and different kinds of molecules.
Right.
So what is for that particular Hamiltonian? It's not for a general Hamiltonian that is K-local. For that particular Hamiltonian, and try different algorithm, try to cast out resource estimation per se, and
that's
cast out the concrete.
Just like that's the nitrogenase fixation. So it's nitrogen fixation that Microsoft in particular has done a bunch of work around resource estimation of what it would take in terms of fault tolerant qubits to do that, to solve that problem, solve that Hamiltonian.
Exactly. And then people get a number like how many gates we actually need on fault tolerant quantum computer, and then we try to bridge the gap between hardware and theory, which is definitely bring up the hardware awareness. Like, can we design our algorithm, say, in a more robust way to certain features of the hardware and how to feed them and so on and so forth.
Or find specific error mitigation techniques that work for your particular problem on this particular hardware. That co-design kind of concept that comes up a lot.
Definitely.
And is that, I mean, that's more of a, in classical IT terms, that's more of like a hacking approach, right? You're just trying to find within the parameters that you have to work with, you're trying to find tricks, basically, to shortcuts or tricks that are going to squeeze more performance out of what you are working with in terms of the equation and the hardware.
That's right. Maybe just one thing to mention that I found fairly interesting, may not be counterintuitive at all, but is when we go from these optimal asymptotic scaling algorithms to the resource estimation, in many cases you will find that for a given problem, for a given precision, and that you want to find, the optimal scaling theoretical on paper algorithm may not give you the best number as an outcome. It really depends, because these are based on the assumption that the system size is super large and the precision is super small. But say for chemical precisions and for actual system size, you may not always find that the best theoretical, the optimal asymptotic algorithm gave you the best number.
Well, and that, I mean, is it right that, am I right in thinking that in classical computing, there's been a similar sort of back and forth between heuristics and like a theoretical advantage, right? I mean, there's been sort of algorithms that have been hit upon that work practically, that took a long time to actually prove theoretically that there was any kind of efficiency there, right? I mean, is there, I guess, is that just sort of assume that there's always going to be this back and forth between heuristics and theory?
Yeah, definitely. That's a great question. So I will share my personal perspective on this. I feel like, people say before we have supercomputers and where our computation power, before we have GPUs and so on, people cares a lot about proving theories, especially in the last century, and we just started. We want to know that these are our guarantees. We are currently really in quantum that stage, and that's why we care about proving bounds and so on and so forth. But I would think if one day we really have super large fault-tolerant quantum computers, just like now we have GPUs, then say people just run on classical computers machine learning algorithm. If they work, they work.
They work,
And no one, people still very much care about proof, but they, not that at that level. Say these big companies, if it works, then great.
It's so, like when the resource is constrained, it matters a lot to do all the theoretical groundwork. But once the resource is abundant, it's like, who cares? Just use it.
Exactly.
Use it. What if it works?
That would be my perspective.
That's
I would
really smart.
think that currently we are trying to prove these provable theorems and so on and so forth, so that we have enough of a motivation so that we can get that level. We can really get a fault-tolerant quantum computer large enough due to
it's
all
justification
these.
Then, in part,
But then I feel like once we really get there and these maybe I will be out of job.
Right.
And I will be very
was gonna
happy
say
about
that.
that. I will be very happy about that if we have we have a fault tolerant quantum computer, and that's
Right.
the reason I'm super happy about that.
What do you do next, though?
Yeah, I can still, I'm
It's a long way in the future. You don't have to worry about it now.
yeah. And also, I think, I'm mainly working on different mathematical tools with applications. I can go find the next exciting applications.
Yeah.
So,
well, and I think, in part, it feels like the motivation behind the level of investment in quantum computing is because there's a general awareness that we're kind of at the end of what we can squeeze out of classical computing in terms of physical limits of the chips and the density of those transistors and et cetera, right? So, I feel like we've been in this very long period of abundance in computing resources. And if it's quantum computing, if it's neuromorphic computing, if it's thermodynamic computing, there's going to be, if anything, more and more sort of diversity in the way that we compute going forward. So you're always going to have some new resource constraint to try to lay the theoretical groundwork around and try to figure out how to best use all these exotic kind of new resources that are coming on the stage, right?
Yeah, that's true. That's true.
That's really interesting. And you mentioned sort of the path forward. You sort of laid out a couple of different, looking at the theoretical, the purely theoretical sort of upper and lower bounds, and then looking at the sort of co-design or the optimize. Are there other areas that need, you think, more focus, more investment of time and resources in this stage of where we are, sort of in the earliest stages of logical qubits and fault tolerance?
Yeah, I think we also have discussions with some other folks at this event, RPI. So I think many of us feel like resource estimations at this current stage should be put more efforts into, because many of these, we have a handful of theoretical exponential separation tasks, including Hamiltonian simulations, Shor's algorithm for factoring, and quantum linear system algorithms, and some of the potential quantum learning problems. And these problems, we already have pretty much the near optimal scaling algorithms. The next question would really be like, for a concrete application, and what is the best in reality for these application algorithms? Different application can have different algorithms as a number. And I guess maybe could mention that's why Google is putting $5 million for their X Prize is for quantum application. I find, I'm very fortunate to be one of the judge on the panel. But
oh, cool.
I find that the public's portion, say my friends who do not work on quantum computing at all, some of them heard about the news. Okay, Google is putting $5 million. This is how news picture it.
Right.
Google put in $5 million to find the quantum applications. So my friends were messaging me, was like, they were freaking out. They were like, does it mean that Google, it must, because we absolutely have no applications for quantum computer. Otherwise, why a $5 million cash prize? I was like, no. We know these are applications, but they were over abstractions, and these were not, from a public's viewpoint. If I do not work on anything scientific, why should I care about Hamiltonian simulation? Why should I care about quantum linear system solvers?
Right.
We need something that is
grounding.
Grounding that public can see that this is maybe, I don't want to pinpoint any particular application, but applications that is not on the scientific level. We have to write an equation to justify what it is doing.
And doesn't, back to your point about sort of like trying to figure out how to get the best performance from the hardware that you have. It feels like a real world problem is part of the forcing function, right? That's part of the constraints that you have to work within. It's like, this problem that industry is facing or society is facing needs a faster solution or a more accurate solution, and those are kind of the success criteria that you need to work towards from an algorithmic perspective.
Yeah,
right?
definitely.
Yeah.
So I personally, so I work on a lot of Hamiltonian simulation, and there were different levels. I think people consider, say, in your error metric, you want to in the first layer of the roadmap that I discussed, the upper bounds, the lower bounds, and whether it's BQP hard and so on and so forth. These are typically looking at the worst case scenario,
right?
Which means you have a Hamiltonian dynamics, and then you look at the worst case observable and maybe the worst case the initial condition that you deal with, and then you try to pick the bad guy, and you try to prove this is very hard. But like in reality, then when we go to the second level, we try to deal with generic problems. So for generic Hamiltonian, not a particular Hamiltonian, not the worst case scenario,
right.
Can you prove a bound? And the third there, I would think this is, many of my research is regarding the bounds, but what I prove a lot is regarding, so if I have a specific problem given at hand, I have a given initial conditions, some given observables, those problem typically has structures, and then you don't have to deal with the worst case scenario. It can improve your bound dramatically in many situations.
But I mean, so like the reason you sort of go for worst case is because that's where you can actually create the theoretical framework.
Yeah, that's right. That's right.
As you said, you sort of set things to zero or to infinity.
Yeah,
basically.
That's right.
That's so interesting. That's really interesting. So, I mean, that's where your roadmap sort of leads to is that, you know, the theoretical grounding and then working out sort of the real world example, and then finding those shortcuts or those heuristics that actually lead to an application, so to speak.
Yeah.
Okay.
I would say that's the case. Yeah,
that's very cool.
Yeah.
So like you're on the judging panel for the Google X Prize, the Quantum X Prize. That's great. By the way, when I was at CERN for the Open Quantum Institute launch just a couple of weeks ago, when Google announced that X Prize as part of the Open Quantum Institute launch, so I think it's really terrific. As you said, it's sort of a motivating kind of and also communicating kind of tool. It's making it real for people. So what you know, since you're judging, you can't actually participate in any of those. Yeah. So what sorts of projects are you working on over that you're looking to bring out results on in the next year or two?
Yeah. So I'm currently working on I do linear differential equations, and in particular, Schrodinger equation is a linear differential equation. So it's one particular case of that. So I have been working on, as I said, typically when people look at the judgment of the cost of an algorithm, and the error metric is typically the worst case scenario. You want to have a quantum circuits, and you can prove that this is a cause, and then it will work for arbitrary observables, arbitrary initial conditions. You just do not take those things into account.
Right.
And what I was working on is for given problems, what are the observables, what are the initial conditions? Say, typically I can prove, in particular, I look at these unbounded Hamiltonian simulation problems. It sounds not a very common word, unbounded. What does unbounded even mean? It's actually just the Schrodinger PDE. So it just means that in Schrodinger equation, we have momentum operators. These operators are derivative operators, differential operators from L2 to L2. That's where the wave function naturally lives in. It is unbounded, because you need the derivative to be bounded in order for, after you take the Laplacian, the second derivative, it is still within a bounded L2. So if you take the derivative of an arbitrary L2 function, the end product will not send you back to L2. So that's why if we look at these, for unbounded Hamiltonian simulations, if we look at for arbitrary initial condition and arbitrary observables, you will always get the operator non-bound, which is the bound of the Hamiltonian operator, is infinity. And why do we even care? The reason is because if you look at most of the quantum algorithm literature, and all of these most of these Hamiltonian quantum algorithms will have at least a linear dependence on the operator norm of H.
Okay.
So once the operator norm of H is infinity, then what does it even mean, right? This is not a problem if we have. So I was talking about this first quantization framework. This is not a problem if we look at the spin system and the many-body Hamiltonian as a many-body polys, the linear combination of many-body polys. Those will always be bounded. However, if we honestly looking at the differential equations, those operators, so first of all, what is the best truncations in the spatial degrees of freedom so that we can prove that with this truncation, so after truncation, we can fuse the size of the Hilbert space, and this is the best truncation. This truncation and will remain holes for the rest of the evolution time. This is very important because in many cases, say in chemistry application and so on and so forth, people will just make this number truncation n as a parameter. And the end cost of the problem will have n as a parameter enter in. However, n is really coming from the error, and then I choose n, which is how I truncate it.
Okay.
So first of all, what is the best truncation, and can you prove a bounds for that? Once the bound is proved, this can equally hold for classical as well. Because, these are...
Is that going to lead to, I mean, are you trying to get a more accurate framework for that resource estimation?
That's right. And then so once we have these truncations, so one may think that unbounded operator is not really a thing because once you truncate it, it's always going to be a finite dimension and it will be bounded. So what's the big deal? It turns out, just look at one dimension, very simple example. It's an oversimplified example.
Simple's good.
Yeah. Just one dimension Laplacian operator is the second derivative. If we try to do the spatial discretization, we'll have a finite dimensional matrix. That's not a problem. So if we use n degrees of freedom to deal with this spatial discretization, can be any of our field, can be plane wave discretization, finite difference, and the different orbitals, whatever. The point is that the degrees of freedom is n, and the operator norm of these operator is also n. However, for n Hilbert space, we know that we only need log of n number of qubits to represent the space.
Okay.
So everything is great. We are doing great on using this quantum circuit, quantum algorithm, and everything is on the log of n. All of a sudden, the operator norm of n comes in. It becomes polynomial of the size. And this is definitely a large overhead that we do not want. So this was very much what I've been working on.
Interesting.
Yeah, it turns out, again, because this is unbounded operators, not every initial condition you put in is making sense because if the initial condition do not have any sort of bounded derivative, this should not be the space you look at in the first place. So what I was able to show is that if we look at the specific initial conditions, and with certain regularities, these are mathematically speaking Sobolev norms estimate that we do. So if these, which means that the derivative have certain structures, derivative remain bounded in time, and how we will prove all of those bounds. And then we can show that with respect to this sort of special class of initial conditions, and we can get rid of this operator norm dependence.
Okay.
And we can recover the log.
Okay. And that's so you're essentially making a step from the purely theoretical to the real world application, because you're assuming any kind of real application is going to have specific parameters. It's not going to be unbounded. It's not going to be those theoretical limits. Got it.
That's right.
That's really interesting. And do you ever, do you work with sort of practical implementations on hardware at this stage, or do you sort of foresee taking it to that level at some point?
Yeah, currently, unfortunately, I do not work with the hardware implementation. But since I'm at Duke Quantum Center, our folks do have asked me, is there any of your algorithm can be implemented? And I'm thinking about that, but I think the current unbounded Hamiltonian, there are various different algorithms. Sometimes I prove a bound for existing algorithm, maybe others developed, or some improved bound, or I develop my own algorithm. But all of those algorithms are very much complicated to... I mean, it does feel like when I've gone to QIP in the past, there's so many interesting papers being presented, but they're all starting with presuming we have quantum memory of a certain size, we'll be able to do that. There's still this boundary of what's practically possible. That's pretty limited, I think. That is right. I think many fault-tolerant quantum algorithms nowadays use maybe either QSVT, quantum singular value transformation, or QSP as a building block. And I would just love to see, say, the QSP alone being very accurately implemented on hardware level. And I think this is very much doable. I can come up right now, a simple example, and write the explicit circuit. And I think that would be a very exciting thing to work with our hardware team at Duke Quantum Center.
Well, you certainly have a lot of skilled practitioners at Duke, so I'm sure Ken Brown and Chris Monroe and
yeah, they are amazing.
Yeah, they really are.
We also have other experimentalists, Norbert Link, and working on very interesting things.
Yeah,
and
that's great. Well, thank you so much for joining me today. This has been super interesting. I've learned a lot, and I have a lot of questions to follow up on, but I've got research to do on my own, so I'm very appreciative. Thank you.
Yeah, thank you so much, Sebastian.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.